Okay, so here's a quick review of Module 2. So the first thing we learned in Module 2 is Ohm's Law. Ohm's Law tells you that if you have a resistor with resistance R, and there's a current I flowing through the resistor, the voltage is just the current times the resistance. So you should think about R in this case as a constant. And it's a constant that depends on the material properties and geometrical properties of the resistor. So resistance is equal to rho, which is the resistivity. And that's an intrinsic property of the material out of which the resistor is made. But it also depends on L, where L is the length of the resistor. So we can model the resistor as a little cylinder with length L. And A is the cross-sectional area of the resistor. So this means that if you increase the length of the resistor, the resistance goes up. And that makes sense because the electrons have to move through more of the material to pass through the resistor. And if we increase the cross-sectional area of the resistance goes down. And you can think of that as, you know, if you put more lanes on a highway, you can get more traffic flowing faster through down the road. So this is an intrinsic property of the resistor, and L and A are extrinsic properties, so they depend on the geometry of the physical resistor. Sometimes you'll hear people talk about conductivity, sigma, which is just the inverse of the resistivity. We also found that for ions in a solution, the conductivity is equal to CQ squared over F, where C is the concentration of the ions in solution. Q is the charge carried by each ion, and F is the drag coefficient. So we also learned that for a conductor, so here's a conductor, if the conductor is in equilibrium, there's no charge flowing. And that implies that a conductor must have the same potential everywhere inside. So we can see that's true because if we have a point here that's 9 volts and we have another point at 0 volts, the electrons are free to move in the conductor, and so they would flow from 9 volts to 0 volts. So it has to be true that if the conductor is in equilibrium, it has the same potential everywhere. Even if there's a cavity in the conductor, it's still the same voltage in there. So if this conductor was in equilibrium at 9 volts, it would have 9 volts here, 9 volts here, 9 volts here, 9 volts here, 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 etc. Then we learned about capacitance. So if you have a capacitor with capacitance C, the drop in voltage across the capacitor is just equal to the total charge on the capacitor divided by the capacitance. And we found that for parallel plate capacitor, the capacitance is just given by epsilon naught times A, where A is the area of the plate, and where D is the separation between the plates. And we found that for an isolated sphere, the capacitance is 4 pi epsilon naught times the radius of the sphere. And one of the great things about capacitors is that they can store energy. So the energy stored by a capacitor is 1/2 Q squared over C, where this is the charge on the capacitor and this is the capacitance. And if you want to write this in a different way, you can plug this in for some of the Q's. And so you can get that the energy is 1/2 Q delta V, or 1/2 C delta V squared. Now, if we have an arrangement of capacitors or resistors in a circuit, we can sometimes rewrite them. So if I have 2 resistors in series, for example, the total resistance of these two resistors in series is actually just R1 plus R2. And that kind of makes sense because, well, suppose we had two resistors that are the same and they had the same length L, and we put them in series. Well, that would effectively just double the length, and we know that if we double the length, we're going to double the resistance. So that makes sense. If we put the resistors in parallel, however, the inverses of the resistance add. So 1 over the total resistance is equal to 1 over each of the individual resistors. Capacitors behave in the opposite way. So if we have capacitors in parallel, their capacitances just add. And that makes sense because suppose we had two capacitors that were the same. Then putting them in parallel is effectively just doubling their area, and so we would have twice the capacitance. But if we put them in series, their inverses add, just like resistors do in parallel.